Welcome to a tutorial of ProfLearn YouTube channel. In this particular video, we're going to have a discussion on stationary waves and how questions have been asked in various years and we're going to see what's the best approach you can be able to use in order to answer questions to do with stationary waves. So in this topic, we are going to have a masterclass discussion of possible ways you can be able to approach this kind of a topic. And if you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to do more tutorials, you'll be notified. So stationary waves is one of the topic that is tested in Unit 3. And one of the area that we are going to focus here is looking at how do we define or how do we state the formation of a stationary waves. Here you are supposed to explain how standing waves can be formed, how standing waves can form on a cable that is fixed in both ends. So something that you really need to understand that if the cable is fixed in two ends and if an incident wave is drawn in that particular cable, the moment that wave travels and reaches one end, that wave is going to be reflected. And when the incident wave and the reflected wave superpose or interfere, then there will be a series of constructive and destructive interference. So if you are asked to state how a stationary wave is formed, you will say a stationary wave is formed when an incident wave superposed with a reflected wave. These two waves must have same amplitude. They must have also the same frequency, but they are traveling in opposite directions. So I responded to that and said standing wave can form when incident wave and the reflected wave from the fixed point interfere. Then when the two waves interfere, we're going to have constructive and destructive interference. Where constructive interference takes place, that's where we are going to have a maximum displacement, and that's what we are going to call an antinode. So a node form where there is destructive interference. And that's going to happen when the crest is coinciding with a trough. So the two waves are going to cancel each other. But if a crest and a crest coincide, this is going to have cause what we call constructive interference, and now an antinode is formed. So we need to understand at the antinode what happens. At the antinode, of course, the highest point where we have the maximum point where we have the maximum displacement, that's what we call the antinode. And this is a region of maximum amplitude, and an antinode is due to constructive interference between the two waves. A node is where we have region of zero displacement, and this is formed due to destructive interference, and we can say it occurs when the two waves are antiphase, having a phase difference of 180 degrees. In strong winds, the Golden Gate Bridge emits a humming sound. One of the suspending cables on the bridge has a mass of 2.10 times 10 to the power 3 kilograms and a length of 87.0 meters. One of the suspending cables on the bridge has that particular mass, and then we are told show that the mass per unit length, which is mu, mass per unit length is 24 kilogram per meter. So meaning for you to find mass per unit length, we are going to say is the mass of the wire divided by the length of that wire. In this case, we're going to say 2.1 times 10 to the power 3 divided by 8.7, and if you work it out, you're going to get approximately 24 kilogram per meter. 24 kilogram per meter. So we're going to see how do you use now that knowledge in order to work out this question. We're told the lowest frequency of the humming sound. The humming sound is, that is the humming sound that we're talking about. Now the lowest frequency of the humming sound produced by the bridge is 280 hertz, and the total mass of the rod on the bridge is 140 times 10 raised power 6 kilograms. The weight of the rod is supported by 50 suspending cables. The range of the length of the suspending cables ranges from 3.5 all the way to 160 meters. The value of mu for all the suspending cables is 24 kilogram per meter, and deduce whether the lowest frequency of the standing wave, we are supposed to try to work it out and check the lowest frequency of this standing wave is going to be what? Is going to be that we have really had here. So deduce whether the lowest frequency of the standing wave on this could produce this particular sound. If the lowest frequency produced by the wire could produce this humming sound, and the humming sound is having 280 hertz, so we're going to check, is the lowest frequency going to be 280 or not? So something that we need to remember first, we need to know what is the tension on this on these strings, or in these suspending cables. Because the cables are supporting the weight of the rod, then the tension on the spring or on the cables is going to be equivalent to the weight of the rod. The tension in the cables is going to be equal to the weight of the rod. That's what we are going to check. Now, since we were given the mass, we can now be able to work out the weight, because we know weight is given by the formula mg. So working out the weight, we're going to get 1.37 times 10 raised power 9 newtons. But since we are having 500 suspending cables, we need to know what is the tension in one over the cables. So we are going to take the total weight of the rod, divide by the number of the number of cables that were there, which were 500, and if you work it out, you are going to get there is a tension of 2.75 times 10 raised to power 6 newton in each of the cable. Now, for us to work out the frequency, we need to know the speed of the wave in the wire or in the cable, so that we can be able to use V equals to F lambda, so that we can be able to use V is equals to F lambda in order to work out frequency. So V, we are going to use this formula. V is equals to a square root of tension over mass per unit length. So basically that is the concept and the formula we are going to use at this given point. And if you are new to Proflan YouTube channel, consider subscribing, so that anytime I'm going to do more tutorials, you'll be notified. As you subscribe, and remember to support Proflan by sharing this particular video to your friends, encouraging them also to subscribe. And don't forget to check our Patreon page, so that you can be able to get the PDF of this walkthrough of this worksheet that I'm having here. So check the Patreon page, the link is in the description, so that you can be able to have it in your file as you are preparing for your exam. So don't forget to subscribe, don't forget to share this channel to your friends. So let's proceed. Now, for us to work out the velocity or the speed in the cable, we are going to use V is equals to square root tension over mu, so that we can be able to get the speed. So you can see this formula here is the one that I've used at this point, and the tension is the tension per cable, and we are going to get 2.75 times 10 to the power 6 over 24, because already we had gotten mass per unit length, and our speed becomes 338.5 meters per second. Now we have the speed at which the wave traveling in the cable. Then we can be able to apply the formula V equals to F lambda, which is the wave equation, and that means we are going to substitute. For us to get frequency, we are going to say V over lambda. So let me just bring to your attention, if you are having, because here we were told the lowest frequency. When is the lowest frequency formed? Is when we have a shape like this. So between this fixed point and another fixed point, when you have a fundamental frequency is when you have a single loop like this. And since in a stationary wave, when you make a complete cycle, that's when you have a wavelength. But if you move a half a cycle, that's half the wavelength. So meaning if the length of the string was 3.5 and because from this point to this point, because the cable was fixed at different ends. So let me just take you straight to that picture that we were having there. Yeah, so you can see if you're having a cable fixed at this given point, if you have a cable fixed at this point and also fixed at that lower point, the lowest vibration you could make is just having this and this one, so it's vibrating like that, huh? So we shall have from this point to this point, we are going to have a wavelength, but we know the length of the wire was given as 3.5 and the other short wire here is given sorry, this is 3.5 short wire in this end, and this end we have 160 wire of a wire of 160 meters, and on this other end we have a wire of 3.5. so which means we can say now, if this is a single loop like that, then this 160 is representing a half a wavelength. So if we want a half a wavelength, so if we can say, if we are saying that a half a wavelength is equals to 160, what is the wavelength of this wave that is going to be formed? Is wavelength is going to be 160 times 2, so this is going to translate to 320. But if you are using 3.5, we are going also to say half a wavelength, a half is equals to 3.5. so wavelength that will be created at that point will be, wavelength is going to be 3.5 times 2, and that's going to translate now to 7. So that's why you can see at this given point here, at this point here, when we are working out V is equals to F is equals to V over lambda, it means we are going to use our lambda. If we want the lowest frequency, of course you use the shortest. If you want the highest frequency, you'll use the shortest wavelength. So meaning instead of 3.5, we are going to multiply 3.5 times 2 so that we have the wavelength. And then if you apply, you are going to get 48.4 hertz. But the lowest frequency is going to be given by the longest. The highest frequency is going to be given by the the smallest frequency, or the lowest frequency is going to be given by the longest wavelength, and that is going to be 160 times 2, that becomes 320. And if you work it out, you are going to get your answers what? 1.06. so we can say 1.06 is less than 280 hertz. So since the lowest frequency is less than 280, then we can say it cannot be produced, because we were supposed to deduce whether the lowest frequency standing wave on the suspending cable could produce the humming sound, because the humming sound was having this frequency. So if you work out the frequency produced by the lowest, is going to be what? 1.06. So we can say it's not produced by the suspending cables. It's not produced by the suspending cables. So changing the gear and looking at another question. So we need to understand the distance between antinode and anode is a quarter a wavelength, and distance between this node and another antinode here is a quarter wavelength. So if you add this length, will correspond to a half a wavelength. So we are told calculate the frequency of the sound produced by the stationary wave. The speed of sound in air is 330. So we were told that the length of the recorder is 23.6. the length of this recorder is 23.6, but this length of the recorder as per the sound that is being produced is going to have a wavelength. So that is something that we have to put into consideration. So for that reason, we can now be able to say that 23.6 equals to a half a wavelength. So if we want the wavelength, we're going to multiply this by 2, so that we are going to have 2 times 23.6, and that translates to what? 47.2 centimeters. So the wavelength of this sound that was produced, or the stationary wave that is produced here, is 47.2 centimeters. Remember, the units here are given in centimeters, so we really need to convert that to meters, and our wavelength in meters is going to translate to 0.472 meters. Calculate the frequency. How will we get the frequency? We are going to use the wave equation, right? Yeah, so if you say V equals to F lambda, and since we have the speed and we have the wavelength, then we can be able to have frequency by saying 330 divided by the wavelength, and we're going to get 699 hertz. 699 hertz is the frequency of the stationary wave that was formed. The recorder is made from 3 separate sections. We have this section and this section and this section, which can slide over each other. So you have a section that can be adjusted, so it can be able to slide into one another, so that you can be able to adjust the length of that recorder. The musician plays the recorder and produce same frequency sound as in Roman 1. So the frequency of the sound in Roman 1 is 699 hertz. Explain how the musician can adjust the recorder to produce the same frequency as shown. So what happens is that the temperature of air increases. If temperature of air increases, the speed of air is going to increase. You see, if speed is going to increase, then the frequency is going to change. So which means we need to do some few adjustment. Look at this formula that we are having here. If the speed increases, then it means frequency also is going to increase, because speed and the frequency are directly proportional. And wavelength, if what will we do in order to reduce the frequency? Because if speed increases, wavelength also if speed increases, frequency also increases. The way we can be able to reduce this frequency is by increasing the wavelength. If you increase the wavelength, you reduce the effect that is caused by the increase of the velocity or the speed. So if you increase the wavelength, you are going to reduce the frequency, so that it becomes this. Because immediately temperature increases, the speed increases, then it means frequency will be high. Now, since the musician need to have the same frequency as this, we need to increase the wavelength. And how do you do? What do you do to increase the wavelength? Remember, length was equals to lambda over 2. How will you increase this wavelength? If you increase the length, basically you are going to increase the wavelength. So basically, what's the musician need to do is to pull these parts apart, so that you increase the length of the tube where the sound is going to be produced. So the way I responded to this, I said to keep same frequency, the wavelength need to increase, so the length of the recorder should be increased. The length of the recorder should be increased, and this is achieved by sliding the recorder section further apart, so that we have a bit longer sections. And if you are getting value from Proflan YouTube channel, consider subscribing, so that anytime I'm going to do more tutorials, you'll be notified. All right, so moving to the next part here. On a violin, a stationary wave is created when a string is plucked. A violin string has a fixed length, but tension can be adjusted. So you can be able to apply a force when you are playing your violin like that, enjoying the music, then the force can be adjusted, but the wire is fixed in two ends. So we can have a wire fixed at this point and that wire fixed at another section. When the strings are plucked, produces a sound of frequency 432 hertz. This string is adjusted to produce sound of frequency 440 hertz. So frequency 1 is 432, frequency 2 is 440. But remember, V is equals to square root of T over mu, and also we have the wave equation like that. So meaning, since we don't have velocity or we don't have speed of this sound produced in the violin, we can be able to replace V with F lambda. So basically that's what I did. So I replaced V with F lambda, but remember, wavelength remained the same in this case because the section, the violin wire is fixed at 2 points, so we can ensure that wavelength remains the same. The tension is going to vary and mu is going to remain the same, mass per unit length. So if you rearrange this equation so that we can be able to have our constant in one section here, so we are going to have F squared. How do we have F squared? If you square these both sides, you are going to have F squared lambda squared. So if you multiply this mu on this side, we shall have this, and we can now replace this guy with a constant K, because mu is constant, lambda is constant. So we shall have our equation reducing to tension is equals to Kf squared. So with this formula that we have here, we can say T equals over F squared is equals to K. So from here we can say therefore T1 over F squared 1 is equals to T2 over F squared 2. So if we multiply this on the other side so that we have F1, F2 and F1 on one side, we can end up having this equation. So we shall have T squared T2 over T1 should be equals to F2 squared over F1, but our F1 was 420 and F2 is 440, so we're going to say 440 over this, which is going to translate to 1.037. So we can now work out the percentage increase, because already this is the increase, so the percentage increase will be the original over the increase, which is 0.037 times 100, and that becomes 3.7% as the percentage increase in that particular point. So basically that's what we are supposed to do in that case. And we can also, you can be tested or a question whereby there is a mass that is hanging on one end, and then if this vibrates, is going to create incident waves are going to be generated along this string, and the moment that wave reaches here, it's going to be reflected, and then we are going to have a possibility of the formation of a stationary wave. Explain how a stationary wave forms on the string. We can say now, when the incident wave generated by the vibrator interfere with the reflected wave at the pulley, because the incident wave will travel to the pulley, then when it reaches there, it's going to be reflected and it's going to travel back. When the two waves are going to interfere, then it means a stationary wave is going to be formed. The frequency of the stationary wave was 30 hertz. The distance between the vibrator and the pulley was 3.6 meters. Point R, which is 0.6 meters from the pulley, is as shown. So the distance from this point R here, we have the point R. So the distance between this point R and the pulley, because at the pulley, that's where we can have a node. Yeah. Anytime you are having a wave and a string which is tied in two ends, it means at the ends of that string, that's where you are going to have what? a node. A node can be on this fixed end, and a node can be also in this fixed end. Then now once the wave reaches this end here, it's reflected back, and when the reflected wave and the incident waves interfere or superpose, then a stationary wave is going to be created. So in that case, that's why we are going to mention that to determine whether there was a node at R. How are we going to determine whether there was a node at R? We need to know the distance between a node and a node. Always a distance between a node and another node is basically a quarter. A distance between a node and another node is usually a half a wavelength. Rather, what am I saying is a half a wavelength. So the distance between a node and a node is a half the wavelength. So meaning, if we are going to get the wavelength of the stationary waves here, we can check is the distance between is a half of that wavelength equals to 0.6 meters. So if we get that a half of the wavelength of this stationary wave is equivalent to 0.6 meters, so it will mean that a node was formed at R. So let us now work at this question. Now we are told that determine whether there was a node at point R. Mass per unit length were given here. So we are told also M. What's M? What's M? What is determine whether what's M? Is this mass that was suspended. And remember, this mass that is suspended is to give the tension on the wire. So we can be able to go ahead and work out the weight of this mass so that we can be able to know what is the tension on the wire. So we can say weight is equals to mass times gravity, so which is going to be 0.3 times 9.81, which is going to translate to 2.94 newtons. Then we can be able to apply this formula: speed of a wave is equals to tension over mass per unit length, and that mass per unit length was given at this given point. So we can be able to get the speed of the wave in the wire is going to be 36.0 meters per second. Then we can now apply V equals to F lambda. So how do you go about that? We are going to say V is equals to F lambda, yes. Then we can be able to get the wavelength because we know the frequency of the sound that was generated, of the wave that was generated. It was 30 hertz. That's the frequency. Then we can be able to substitute V over frequency, and we get the wavelength of the wave, or the stationary wave in this particular question was 1.2. But we have agreed that the distance between a node and another node is going to be a half a wavelength. So if we have gotten our wavelength to be 1.2 meters, then a half of that is giving us 0.6, and yet we know at the pulley there is a node formed, and we were told a node could be formed at R. Now, since the distance we are having between this point, the node and R, since it's the same as 0.6, then we now agree a node could be formed at point R. Basically, that's what you are supposed to do in that question in order to scoop those particular marks. All right, so moving to part C, and in part C we are told mass M was changed and the frequency of the vibrator was adjusted so that stationary wave formed on the strings. Adjacent nodes were separated by 0.4, so adjacent from one node to another is 0.4 meters. The diagram shows 2 point S and T on the string at an instant when the string was straight. So basically what I decided to do, I decided to draw a representation of whatever string that we are having here. So where we have a node and where we have the next node, because we are told we have a node at this point and we have another node in this point. So S is 2 meters, 0.2 meters from this node. So meaning this point S is at the maximum point, so our S is going to be at the antinode, because we were told from this node to this node is what? A distance of 4, 0.4 rather, 0.4. So meaning if from here to here we have 0.2, then this must be the antinode, the maximum point. Then we are also told T is on the other side of this node. So if this is the node that we're taking, is 0.1 meter. So it's going to be somewhere not at the antinode, because here we have the antinode. So which means that our T is going to be somewhere here, isn't it? Yeah. So we are supposed to explain the phase relationship between S and T. So what I need to mention is that anytime you are having a stationary wave, or point between the two nodes, any point we will have here, any point here, or this point that we are having here, they are moving in the same direction. All these points that are here are in phase. If you are asked a point at this point, or here, or here, or here, all these points are moving in the same direction. All these points are in phase. But points on this other side also, if you have any point along this loop, also they are in phase. But if you are comparing a point in this region and a point on the other region, those 2 points are exactly out of phase, they are anti-phase, or they have a phase difference of 180. So a point at this given point and a point somewhere here or somewhere here, they have a phase difference of 180. But what can vary is the amplitude, because they are in different positions, they are not in this maximum point. So S and T, they have a phase difference of 180 degrees. They are antiphase since they are in adjacent node regions. Explain how the amplitude of the vibration of the string at S compare with the amplitude of T. So since this is at the antinode, and this is somewhere before reaching the antinode, so we can say S has got a larger amplitude compared to T. So we can say S has a greater amplitude since it is at the antinode, while T is between the node and antinode, so it has a less amplitude. Question number 4, we are told the photograph shows a musical instrument called panpipes. And then we are told the instrument is made using pipes of different lengths. Blowing air crosses the top of one of the pipes and produces sound. A student connected a microphone to an oscilloscope, and then she then placed the microphone near to one of the pipes, and the photograph below shows the oscilloscope screen where the pipe was placed, or producing where the pipe was producing a sound. Then calculate an accurate value of the frequency of the sound, and you are told that 1 division is equals to 1.2 milliseconds. So the point is, you are supposed to check what is the time period for one complete cycle. What is the time period between this point and this point? So we need to find the time period, and I got my time period to be 2.4 times 10 to the power 3 seconds. And then from there I said frequency is equals to 1 over t, 1 over period. So I worked out and I got my answer as 416 hertz. and we have our frequency as 416 there. Each pipe is open at the top and closed at the bottom. When air is blown across open end, the stationary wave is formed. The student was able to produce two sounds from the same pipe, and the diagram shows the node and antinodes A and the stationary wave that caused each of the sound. So there are two case scenarios. You can have a sound being generated like that, and you can see now from this is antinode, and a node is formed at the closed end. Then we can see now a distance between antinode and a node that is a half a wavelength. Yeah, so for instance, if you are having a stationary wave like this, we said if you are having a stationary wave that way, then we are going to have a half a cycle. We shall have a complete cycle. So from this end to the other end, we have a wavelength. But between now a node and another node, this is a half a wavelength. But between a node and antinode, that is a quarter a wavelength. Antinode and a node, that distance you can see is half of this, a quarter a wavelength. So here we are having antinode, we have a node here. So this length of the pipe is going to be equivalent. If you know the length of the pipe, it's given, then we can say the length of the pipe is going to be a quarter of a wavelength. But in this case, we are having a node and we're having a node, so meaning from here to here is a half a wavelength. This is a half a wavelength, and from a node to antinode is a quarter. When you add those guys together, you're going to have 3/4 of a wavelength. So I believe we are together up to that particular point. Then explain how the frequency of wave 1 compare with the frequency of wave 2. This is wave 1 and wave 2. So we can see wavelength of wave 1 is 3 times wavelength of wave 1. Wavelength of wave 1 is 3 times the wavelength wavelength of wave 2. Since speed of the wave in these two types is going to remain the same, then what is varying is wavelength and frequency. So speed remains the same because the same medium, same air that is in the pipes, then the wavelengths are different. So what will change here is the frequency and wavelength. So speed remains the same. So you can see now, if V is equals to F lambda, then F is equals to V over lambda. So if this is constant, if you increase lambda, you are going to have smaller frequency. So if this one will have less frequency and this one will have more frequency because it has a shorter wavelength. So we therefore can conclude and say, since speed of the wave is the same, the frequency of wave 1 is a third the frequency of wave 2. Yeah, so basically that's what we are going to say in that given point. So if you have gotten value, check in the description. I've added a link that's going to take you next to these other questions that we are having here, and also you can check in the Patreon page so that you can be able to get the PDF of this worksheet so that you can also keep on working. So I believe if you have gotten value from ProfLearn YouTube channel, consider subscribing so that anytime I'm going to do more tutorials, you'll be notified. Anytime I'm going to do other videos, YouTube will be able to notify you immediately. So I wish you the best of luck in your coming exam. See you in the next video.